So, we will enter into this session with a very important topic, and this is a topic where we will now move from the fluid dynamics to a set of problems which in a very loose sense we can call fluid dynamics plus plus. That means, there is fluid dynamics and there is something else, and that something else in a fluid dynamics problem can be really widely varying. There are many problems where you have electrodynamics, some problems you have electromagnetohydrodynamics, some problem optics may be involved. So, it is literally unbounded in terms of what kind of physical aspects can be covered. But in the mechanics paradigm, something which is perhaps inevitable in the physiological system is this one, which is fluid structure interaction. So, by structure we mean solid. This name fluid structure interaction came into the description of the subject because this was originally developed by engineers who were working with fluid mechanics and structural mechanics. So, maybe civil engineers, aerospace engineers, very commonly they have to deal with fluids and structures and they are interacting. Having said that, when the physiological flows came into the realm of CFD, this also became very important. And in fact, the Ansys platform that we will be using to solve such problems, one of the great advantages is that the Ansys platform was already existing for its applications in solid mechanics and Fluent was there for fluid mechanics. So, when they merged, it became like a natural platform to work on problems where both fluid mechanics and solid mechanics, they are not only involved, they are coupled. So, we will look into some of the fundamental aspects, and then beyond that, that is how you apply your numerical simulations to solve those problems. So, I have noted down some applications of fluid structure interaction in physiological flows. Cardiovascular hemodynamics. Hemodynamics means blood flow dynamics in the human body vessels, that is called as hemodynamics. So, cardiovascular hemodynamics is what I would say the most common topic which we would imagine as an application, because you have a large number of blood vessels all across the human body and they are deformable, and arterial deformation is in fact very important, because that leads to certain conditions which may be very important for stroke, heart attack, etc., and these are not yet very well understood. People, I mean, medical science has advanced definitely, but even now if you ask most of the advanced doctors with most of the advanced facilities, there is no way people can predict a massive cardiac arrest which can happen at any point of time. So, it is important to really research more about that, like with respect to heart you have mechanics of heart valves. So, you have the heart valve and the heart valves will open and close and how they are performing, and it is very important to understand that, because if you are designing a prosthetic or artificial heart valve, you must be having a whole lot of understanding and control on the real physiological heart valve, how it works. If you understand it well and then if you use the proper material and design it, it will definitely serve some good purpose. Respiratory flows, we have already talked about this. So, you have airflow and lung tissue deformation, and so it is not just airflow or the exchange between the gas and the blood, but more in a more subtle manner you have the lung tissue deformation also very important, which which has to be taken into account if we are trying to understand diseases such as asthma, for example. Vocal cord dynamics. So, interaction between airflow and vocal cord and its vibration. So, let us say that someone who needs voice therapy. Now, I mean these things are very typical, because nowadays the treatment has become so good, say someone is having a kind of I mean some issue in the vocal cord, so that the maybe the vocal cord does not work, maybe there is some tumor or something like that around and it has to be operated. So, if it is operated and it has stopped functioning, then there can be an artificial way of stimulating it, and if you understand the mechanics you will know that what are the things to be done, like voice therapy and speech synthesis. In fact, if you are using AI for voice therapy or speech synthesis, the data can be generated from some of these inputs. The GI motility, that is gastrointestinal. So, you have a peristaltic movement in the digestive tract. We all know that in the esophagus you have that peristaltic movement. So, if you have that and if you understand it properly, then if there is some issue with that, the esophagus or the food pipe, and then that can be rectified. Aneurysm development is one of the major problems in cardiovascular disease, like there can it can also lead to very narrow passage, the entire arterial space may be large, but because of this plaque formation and all you may really have a narrow space, and that is where actually all the resistance against the flow occurring, and all those plaque deposits and all, they are deformable materials, they are not rigid materials. Blood brain barrier is very very important. So, interaction between cerebrospinal fluid flow and brain microvasculature. So, you have a nervous system where you have a cerebrospinal fluid, and we have not talked about cerebrospinal fluid and its flow as a part of the illustration examples, but that is also a very important part. And the cerebrospinal system, or what we call as the nervous system in general, you have lots of additional things, like you have the sodium potassium exchange, so you have ion transport. So, all these things which come up along with the blood flow. So, overall you see that there is a lot of complexity, and in each of those passages the main focus is you have fluid flow and you also have deformation of the boundary, that is the common thing. Venous valve function. So, I talked about in the introductory session that you have the these valves in the veins which will not allow the blood flow in the opposite, in certain direction it will flow and not in the opposite direction. So, how the venous valves regulate blood flow and prevent backflow under conditions where the pressure can vary. So, that mechanics. So, these are all very important, because more and more you understand, more and more you get handle on if a disease is occurring why, and then you can treat it better rather than sort of giving a heuristic view of that. So, accordingly if you consider different application domains which are related to healthcare, I am not talking about not related to healthcare, because our focus of this course is healthcare. So, to summarize, you have solid, you have fluid, and fluid structure interaction is really the intersection between the fluid and the solid analysis. And if you want to do that, there are ways. One is the grid based, so that just what we talked about in the finite volume. So, you have a grid or a mesh, and if that mesh is a fluid domain, you should give some provision that that mesh is not fixed, but it can change over time. You can also have mesh free method, that means you are just having points to represent the domain, but no mesh as such. And you also have other things like interface coupling, that means you have a fluid, you have a solid, and you do not care about what is there inside the fluid domain and inside the solid domain, you primarily look into the interface to create the coupling and focus on the interface. So, its relevance in biology we have talked about, but one of the very interesting and emerging areas which is not biology but biologically inspired system is soft robotics. That means robots, but maybe tiny deformable entities which of course do not give an imagination like as if they are looking like robots, but they are, you can say, programmed entities which can even get into navigate in the human body, and even they are used nowadays for some very high level surgery, and you have a computer control movement. So, maybe there is an intricate tissue somewhere where the doctor wants to operate or visualize and operate. Now, that is not always easily accessible to a doctor, but doctor has the overall understanding. So, through an entirely computer control system, that soft robot is moving and it is doing its task. Maybe it can also deliver certain we call as cargo in the human body, may be drug or some medical item. So, in that way that is a very emerging area where you can say fluid mechanics, solid mechanics, robotics and AI all are getting integrated and applied to such applications. So, if you now see overall that what kind of problem we are looking for. So, one is that the channel flow or the capillary flow that we talked about, we can imagine that it is the same except the wall of that channel or capillary is deformable, which is like the blood vessels in the human body. So, you can see the left hand side picture that you have a solid domain, you have a fluid domain, and in that way you will have an interface, and interface will evolve with time. So, you have a fixed deformable domain which is the solid domain, but this fixed and deformable in a sense that it is identified, but its interface can vary with time. Now, you have a moving domain means that the entire deformable entity is moving. Let us say you have a deformable capsule or a gel type of material. So, that is an entity which is moving in the stream of a fluid. So, that is also fluid structure interaction, but there the solid itself as an entity is having a bulk movement, whereas if it is a wall it is not having a bulk movement, it is having a displacement. So, for the wall it is more like, say if you consider like mechanics of materials like beam or this kind of thing, where the beam is not physically accelerating, it is just having some displacement, whereas this is like you have its physical movement from one place to another place. So, the strategies are related, but a bit different, and these are just to highlight some application use cases like cardiovascular biomechanics, which is the interaction between blood flow and vascular walls, and we will talk about this in our subsequent sessions. Tomorrow we have a session on this, that how we can predict the cardiovascular biomechanics. You can see this is one of the main arteries and it has its own branches. So, how we can get a visualization of the wall shear stress. So, this is very important because damage to the wall is related very strongly with the wall shear stress, and maybe there is MRI or CT scan or whatever, nothing can give this wall shear stress. So, this is very fundamental. Respiratory system, the interaction between the airflow with the lung tissues, and if you understand this properly, then you understand the mechanism of gas exchange, and you have cilia in the respiratory tract which are there and they are controlling the movement of this. So, that is also because it is dynamic, it is the fluid structure interaction coming into play. So, heart valves, I have talked about this, that if you have either the natural heart valve or the prosthetic heart valve. So, it is very important to understand how the flow in the blood is taking place under the pulsatile nature, because heart is always having a sort of peristaltic, it is like expanding contracting type of movement, which is like giving rise to systolic and diastolic phases. And optically powered tissue engineered soft robotic swimmer, this I talked about as one of the examples. So, there is something which we call a swimmer. So, a small thing which is moving in a fluid stream, it can be anywhere inside the human body, and its effective locomotion and manipulation. So, it is like as if there is something swimming in the fluid inside the body, in any system, but it is it has to be controlled from outside. So, that is where we call it like a soft robotics, because it is controlled, it is automatically controlled, not that it is just you are releasing it and it is moving with the stream. So, how that control will influence the flow and the motion. Now, with all these we need to understand the subject from a bit of fundamentals, and that is all what we have been trying to do for all the topics in this particular course, that if we do not get into complete elaborate things because of the interest of time, but at least the fundamental aspects we touch upon, so that you can get into deeper with the help of that fundamental knowledge. So, when you have a material, what I am trying to deal with is the concept of stress, and why we need to generalize it a little bit beyond the fluid mechanics is because be it fluid, be it solid, the stress is something which is the key when we couple their interaction, both stress and strain, but we here give an example of stress. So, imagine that you have a chunk of material which is shown schematically in the figure. So, this chunk of material it is interacting with the rest of the material. So, it is a say it is a chunk taken from a larger piece of material. So, when I say material, I am telling it very purposefully, I am not calling it fluid or solid. So, this is what is the backbone of a subject called as continuum mechanics. That means, you are treating the material as a continuous medium. So, not like atoms, molecules like that, and not that always media can be treatable like that, but if they are treatable like that, your advantage is that you can then have a description of certain functions which are continuous functions over space and time. Typically for fluid we talk about velocity, and typically for solid we talk about displacement. So, when we have that, so what is responsible for all these? So, there is some force, and the force is giving rise to an effect which is stress. So, before getting into that, let us imagine that this delta F is the net force which is exerted by whatever is there in its surrounding on it. So, this is like a free body diagram, you have isolated it from the other part of the system and representing the force. So, this is like a reactive type of force rather than active force, and it is acting over an area delta S which has a normal direction. So, what we are trying to calculate is we divide delta F by delta S and take the limit as delta x tends to 0. So, we have to imagine that it is not really delta S tends to 0 in the literal sense, because it is just in a conceptual sense that tends to 0 means the smallest one up to which this continuum can be taken as an assumption, because if you take it really to that limitingly small, then you have atoms and molecules as individual entities dictating the what is going to happen, entire this continuum mechanics will not work. So, with that small delta S, if you take the limit, then what you get out of this is called as a traction vector, which conceptually is like force per unit area. Now, we symbolize it with a subscript and a superscript. So, the subscript I, it is the direction of the particular component. Any vector we can use one subscript, say I, with I equal to 1 mean x component, I equal to 2 y component, etc. So, 3 components you can represent. So, in that way a vector will need one index for its description. But here you see that not just that index I, but we also use an index superscript n. What is this? This is the normal to the area ds. Why is it important? Because this calculation of this limit is not just dependent on what is the magnitude of ds, but also how the delta s or how the delta s is oriented. because if delta S is oriented differently, then at the same point you will get a different delta F. So, that is why you have to specify that n direction also. So, now you have something which is called as a traction vector, but it is not as ordinary as any other vector, because it requires two indices. One is its direction like a vector, its component like a vector, but also the direction of the surface at which you are calculating it. So, now when you have such a system, you can describe the force per unit area with respect to a normal. Now, you cannot generalize it. Why you cannot generalize it? Because your surface on which you are doing the analysis can have any possible normal direction. So, you cannot have a general description for that, because if your direction changes, everything will change and you really do not know what is the value. So, it would be very nice if we use some parameters for which the direction is fixed, and then using that describe the phenomenon on a surface for which direction is arbitrary. So, direction fixed means you can, for example, construct that cuboid has its normal directions either along x or along y or along z. So, if that be the case, then the traction vector is represented by again something which we call as stress tensor. In books you will either have tau or sigma to represent that commonly, with the two indices I and j, where I is the direction of the normal and j is the direction of force. In the general traction vector description, the direction of the normal is arbitrary, but in this specific case the normal is either along x1 or along x2 or along x3. So, normal is fixed. So, accordingly you have the nomenclature, like to illustrate the nomenclature I have put this in the diagram. So, for example, if you look into the right face, its normal direction is x2. So, the first index tau, so what you have is you will have there is a little bit of it is just reversed. So, it is reversed, I will tell you why, because it is just in advance it is written. So, tau 2 you can recognize, the first one is the normal 2 and second one is the direction 2. Whatever is the upper, it is like it is fundamentally tau 2 3, because the normal is 2 and the direction is 3, but why it is written as tau 3 2 in advance, because it can be shown that tau ij equal to tau ji, that is why, but fundamentally it is different. So, in that way, so this is one nomenclature, but you can also have like instead of 1 and 2 and 3 you can write x y z, and sometimes when you are having the two indices same, what it is indicating is indicating normal stress. So, sometimes normal stress is symbolized as sigma, and if two indices are there, instead of repeating them just one index is written. So, accordingly many books write simplified this notation. My objective of showing different notations is just to make you bit clear that notations may be different, just learn the concept, and if different books have different notations is okay, I mean that is not a big challenge. Now, keep the basic quest here in mind that we have an arbitrary surface. So, when we have an arbitrary surface, the arbitrary surface has a direction. Let us say that n is the direction of the arbitrary surface. So, when the arbitrary surface has a direction, can we express the force on the arbitrary surface per unit area, which is this T, in terms of the tau ij, which is a standard notation and it can be applied always, because I and j are either 1, 2, 3 like that, it is not arbitrary. So, to do that we construct this diagram where you have 4 faces, right. So, these 4 faces are, one is AOC AOC, another is AOB, another is OBC, and the fourth one is ABC. Now, where is the motivation of taking such a volume to do the analysis? So, if you look into this carefully, out of the 4 surfaces, there are 3 surfaces where the normal is either x1, x2 or x3, like OAB, OAC and OBC. The normal is either x1, x2, x3. So, you can use the tau notation, tau ij, but the 4th surface is ABC, where the normal is arbitrary. So, if you write a force balance over this, then the generalized surface, whatever force is acting on it, can be expressed as a function of the forces on the other surface, which can be written in the tau ij notation. So, let n be the normal to that ABC, where the direction cosines are n1, n2 and n3. So, we are now applying a force balance on this one. So, if you see that the force on let us say AOC. So, AOC is a plane which is the x2 x3 plane, x3 is somehow it is not visible clearly in the slide. So, the axis which you do not see very clearly, that is x3. So, AOC is there on the x2 x3 plane. So, what is its normal direction? x1, right, and in fact negative x1, because normal to a surface is always taken as outward normal, okay, that is the sign convention. So, along that direction, what is the force per unit area? So, then you can use the tau ij notation. I is here 1 because the direction normal is 1 and j is also 1. So, along the x1 direction, the force is per unit area is tau 1 1, and let us say S1 is the surface area of AOC. So, the force, total force is per unit area into the area, and minus sign because it is in the negative direction, okay. Then you go for let us say you go for OBC. So, OBC has direction normal in what direction? x2 minus x2. Now, along the x direction, if you write the force, then tau, the first index is normal. So, tau 2 because normal is x2, and the force direction is the next one, which is 1. So, it is tau 2 1, that is the shear force. So, tau 2 1 into that area is S2, and again minus because its normal is in the minus direction. Similarly, tau 3 1 S3, which is for the AOB surface, and the fourth surface is ABC, for which you have what you call as that the force whatever is you are seeing as minus sign, just correct it, it is plus, okay. Somehow for writing it has become it is a typo. So, when you have this fourth surface ABC, let us say that it has a normal n. So, what is the force per unit area on that? You use the traction T notation with superscript n and subscript 1 because you are talking in the direction 1, and by default it is positive sign convention. If its value comes minus, then it is negative. So, that will be plus this T1 n times S, S is the area of ABC. Then, so this is the surface force, the body force is the volume of this into the force per unit volume. So, what is the volume? So, if H is the perpendicular distance from O to ABC, then its volume is 1/3 into area of the base into height, right, that is the volume of such a thing. So, 1/3 into S into H, and B1 is the force per unit volume. So, you multiply that with B1 to get the total force. So, you have surface force and body force, sum total of this, and as per Newton's second law, this is mass into acceleration. So, mass is density times that volume times acceleration along 1 A1. Now, what you can do is you can write S1, S2, S3 in terms of S. In fact, you can imagine say AOC, it is the projection of ABC on the x2 x3 plane. Okay. So, projection means basically you can calculate it by the dot product of the normal vectors. So, the normal vector of ABC is n and the normal vector of AOC is I. So, if you take a dot product, then it will be n1. So, that is why S1 is S into n1. Similarly, S2 is S into n2 and so on. So, if you substitute that, then S will cancel from both sides and then you take the limit as h tends to 0. Why? See, you are interested to write an expression at a point, whereas you have started with a volume. So, a volume will shrink to a point when? A volume will shrink to a point when the height, that h, is in the limit tending to 0. So, now if you clearly see the expression, when h tends to 0, the body force term becomes tending to 0 and acceleration term also tends to 0. So, you are left with T1 is tau 11 n1 plus tau 21 n2 and plus tau 31 n3. So, this is for 1. So, instead of 1, if you have I as a subscript, so for the ith direction you have Ti, sorry, you have Ti is tau 1 I n1 plus tau 2 I n2 plus tau 3 I n3. So, Ti is summation of tau j I nj, right, and because j is repeated as per Einstein's notation, it is just tau Ti is equal to tau j I nj, we do not write this sigma. So, this is known as Cauchy's theorem, very powerful, because what it is doing, you have any arbitrary surface, it is representing the force on that arbitrary surface in terms of the stress tensor components, which are on some fixed reference direction, and then it can also be shown. So, this is from force balance, then from so linear momentum, from angular momentum consideration you can write tau ij equal to tau ji. I am not sort of repeating that here, just for the interest of time. So, that is how the Cauchy's theorem will finally become Ti equal to tau ij nj. Okay. So, now we go to the equation of equilibrium or motion, whatever you call. So, I have written Navier's equation of equilibrium, you can also call it as Navier's equation of motion. So, equilibrium is a very general term, even motion can be thought of as an equilibrium, people may call it dynamic equilibrium instead of static equilibrium. So, now you see that why I have gone through that is because we are trying to generalize fluid and solid. So, up to this I have purposefully told material, be it fluid, be it solid, any particular property of fluid or solid we have not used. So, now what we are going to do is we are trying to integrate it over a volume which could be a fluid or could be a solid. So, the force when you integrate, one is the integration of the surface force. So, you have the tau I as a vector which is per unit area. So, tau I is tau I1 I plus tau I2 j plus tau I3 k, dot with the normal vector, and in fact if you just write it. So, if you take the dot product, what it will be? So, n is n1 I plus n2 j plus n3 k. So, if you take the dot product, it will be tau I1 n1 plus tau I2 n2 plus tau I3 n3, that is the Cauchy's theorem, the total traction vector. So, this dot product mathematically represents the same expression which in the previous slide we derived, and that times dA, dA is the surface small area, you integrate over the entire area, and that is the surface force. Body force Bi is per unit volume, so that you multiply by volume. So, I have used a bit of a different symbol for volume because otherwise it may confuse with velocity, which we also use V in fluid mechanics or even solid. So, now your Fi is now what you can do is, see, in the right hand side there is one term which is volume integral, another term is area integral. So, what we can do is either convert both into area integral or both into volume integral. So, here we want to convert both into volume integral, and to do that the first term we have like f dot n dA by divergence theorem, Gauss divergence theorem, it is divergence of f dV, where f is that tau I vector. So, if you take divergence of that, so you have tau I and divergence is like partial of j with respect to that. So, it becomes like you can write it as either divergence of tau I, or in the last what you see in the box partial of tau I j x j, right, either way. So, now you have both the terms in the expression for force as volume integral. So, integral of something dV. Now, the force is mass into acceleration. For fluid, mass is volume, density times that volume, and acceleration is AI. Now, where the fluid is differing from solid is Lagrangian and Eulerian description. So, for fluid we are using the Eulerian description for acceleration. So, the total derivative capital D dt, whereas and so that is one expression. So, capital D ui capital D dt of ui is AI. Now, you can write that also in this bracket what we have written, because you can couple that with the continuity equation and then combine the terms together as a product rule of derivative, and then you get this form which is the conservative form. It is important because in the numerical method we are using the conservation principle. For analytical work we typically use the non-conservative form, that is just the total derivative in the original expression. So, for the force equal to mass into acceleration, so you can write that mass into acceleration also as an integral of something over the volume. For solid, let us say that you have rho s as the density of the solid, so rho s into dV into AI, and for solid because we are using that Lagrangian description, it is just the second order time derivative of the displacement SI. So, that is Lagrangian description. So, this is where only it is differing, otherwise you see Navier-Stokes equation is just like Newton's second law of motion. So, then because your, so both the expressions if you see now, if you write the left hand and right hand side, integral of something dV equal to 0, and because that something is arbitrary, then only possibility is I mean not something, that volume dV is arbitrary. So, because your volume dV is arbitrary, that something has to be 0. So, that gives rise to the equation of motion for fluid mechanics in the left and solid mechanics in the right. Okay. Absolutely the same, only the way in which you describe the acceleration is different, one Eulerian, another Lagrangian. The stress also we have written as just like stress, because this is where also fluid and solid is different, because for fluids usually stress is written as a function of rate of strain, for solids it is written as a function of strain. So, rate of strain is related to velocity and strain is related to displacement, and that is why for fluid mechanics velocity is important and for solid mechanics displacement is important. So, why I am emphasizing on this is because I have also been a student like all of you, and what I have recognized from my own experience as a student is everywhere there is so much of compartmentalization that the way in which fluid mechanics is taught and the way in which solid mechanics is taught, it appears to be a different world to the students. In fact, the specialization is different in the department and mostly those professors do not talk to each other except going for tea coffee, and one will always say that they are most important. So, solid mechanics people will say that they are very important, fluid mechanics will say they are important, and because solid mechanics is mostly using finite element they will say that is the best method in life, and fluid mechanics will say finite volume is the best in life, and that is how people do quarrels, but they are the same. You are wearing the two different dresses, one is the dress of Professor Euler and another dress of Professor Lagrange, but the heart and soul is the same. So, you are having these two differential equations where two major differences are there, please make a note of this. One is, in one case velocity is the primary variable, in another case displacement is the primary variable. In one case you have the stress written in terms of rate of strain where the velocity will come, gradient of velocity will come. In another case stress is written as a function of strain where the displacement will come, and this general formulation is very good because see the world does not have always a fixed boundary. We say, so when we describe people we say he or she is a very good person, and we are usually extremists, the other option is he or she is a very bad person. We never say that he or she is a human being will have good and bad qualities mixed together, and that is all humans are, nobody is absolutely good or absolutely bad. So in the world there are many materials which are neither solid nor fluid, so called classical solid and classical fluid, and classical fluid will have viscous behavior and classical solid will have elastic behavior, and there are many materials typically in the physiology and bioengineering application which are partly viscous and partly elastic behavior, that is called as viscoelastic material. So when you have a viscoelastic material your stress is a function of both strain and rate of strain. Stress as a function of strain will be due to the elastic behavior and stress as a function of rate of strain is due to the viscous behavior. Look into a cell inside a human body. A cell has a membrane which has elasticity. In addition to several other properties, membrane also has a bit of viscous behavior because membrane has some gel type of material and which has a viscous behavior. But inside the cell you have cytoplasm which is the liquid, and that will be primarily viscous. So overall the cell will be a classical example of a viscoelastic material in a physiological system. In the engineered system you have almost all polymers are viscoelastic materials, and polymers are very important in bioengineering, or polymer like materials like gel like materials, hydrogel for example. So it is very important therefore to develop a balanced purview of fluid and solid and do not get into an extremist of an impression like a fluid or solid. So if you want to do fluid structure interaction, this is what I have summarized. So you have, there are two possible ways. One is one way coupling. One way coupling means what? You do fluid analysis, the fluid analysis gives an input, and with that input you want to do structure analysis, but do not give that feedback back to the fluid analysis to rectify it, because the fluid analysis was done on a structure, but the structure is a deformable structure. So when its deformation is known, then before the deformation was known whatever was the answer, now the answer will change, and that is how it will be dynamically coupled. So that is a two way coupling you see that you have. Now how it is dynamically coupled? See, every subject, this I keep on stressing that there will be lots of maths, integration, differentiation etc. In mechanics type of subject it is like that, but with that what you say either a burden or a joy of doing integration and differentiation, never lose the most essential message. If you keep that in mind, you will, your integration differentiation also you can make the life simple. So when you have a solid and a fluid, how they are interacting? So remember that on the surface of a solid you will have a normal stress and you also have a tangential stress. Now that normal stress is passed on to the fluid as a pressure on the fluid. So whatever is there as a normal stress on the solid body, at the same point it is minus of pressure in the fluid. Why minus? Because normal stress by definition is tensile positive, but pressure by definition is compressive, right. So the main important thing is fluid pressure on the surface or fluid normal stress, which also could be viscous normal stress, but we will see that viscous normal stress is not as important as pressure in most of the problems. So to therefore analyze this, what you require? You require governing equation for fluid. I have given a simplified example of incompressible flow, just to make it simple. I mean, otherwise long equations will be there. The structure, and I have not written the tau expression because we have already seen that for Newtonian fluid, what kind of expression is there. So, I have not written it separately. For the structure, exactly the same thing what we have derived just now, just to distinguish between the stress in the fluid and stress in the solid, so that the notation does not confuse us. I have kept tau for fluid and sigma for solid, just mentally we know that they are different. So, just like for a Newtonian fluid which is homogeneous and isotropic, we use two parameters. One is the viscosity of the fluid, another is the volumetric dilation coefficient of the fluid. For a solid also, for a linearly elastic solid, we use two materials, two material properties. So, the two material properties here are lambda and g, which we have used. Someone can use, instead of lambda and g, something else which is more commonly studied in the undergraduate, that is modulus of elasticity and Poisson's ratio, right. And lambda and g were mathematically used by the early developers of this solid mechanics subject, and that is why it is still continued for analysis. These are called as Lame's parameter, lambda and mu, whereas this modulus of elasticity and Poisson's ratio are more physical parameters. When measurements came, modulus of elasticity of a material you can measure and Poisson's ratio you can measure, and these also you see has a lot of similarity with the Newton's law of viscosity. So, Newton's law of viscosity, you have a component of stress which is linearly proportional to the rate of strain, and here you have a component of stress which is linearly proportional to strain. In the viscous fluid, there is a component of stress which is related to the volumetric strain rate of the material, which is 0 for incompressible flow, and the corresponding term is there for the solid. The next term, which is you have the trace of the epsilon, that is epsilon 11 plus epsilon 22 plus epsilon 33. So, if you write it in the form of a matrix, the diagonal sum of the diagonal terms, that is the volumetric strain. So, the first term is related to linear strain and the second term is related to volumetric strain. For Newtonian fluid, you have similar first term and second term. First term is related to shear strain rate, or maybe also linear strain rate, and second term volumetric strain rate. So, you see lot of similarity in the mathematical form. So, loosely if you just keep in mind that for solid I care about displacement and for fluid I care about velocity, you actually have got the essential feel of what you are working with. And the coupling, how do you do the coupling? So, there are two important boundary conditions, one is a kinematic, another is kinetic. Kinematic means that wherever you have the connection between the fluid and the solid, the velocity of the fluid should be same as the velocity of the solid point. It is like Eulerian and Lagrangian description merging at the point. So, velocity of the fluid is u, and the velocity of the solid in terms of Eulerian description is the derivative of s with respect to time at that point. So, partial derivative, and they are the same, right. And the force balance is that the stress dot with the normal. So, that is then that is, so because this is the normal stress balance, as I told that the normal stress in the fluid is equal in the solid is equal to minus of the pressure, that is what it is writing in a general form. So, taking the dot product with the normal direction means it is taking only the normal component. B is the body force per unit volume, whatever small b I had written in the previous slide, that is this b. Okay. So, now see all these problems can be solved numerically, and most of these problems are to be solved numerically because you understand the complexity. The domain is dynamically changing, but there are simplified problems which you can solve. So, this is one particular example. Say you have a channel and the channel has a deformable wall. So, when you have a channel with a deformable wall, it is a very common problem which you are talking about when you are considering a bioengineered material which is mimicking the behavior of blood vessels inside the body. So, you have a channel which is say made of some engineering material which is a soft deformable material and the wall is deforming, and sometimes it is very interesting to study this, as I told that you have topics like organ on a chip, human body on a chip. So, there you should also have blood vessel on a chip, and that blood vessel on a chip can be something like this. Sometimes the top is a rigid wall, because many times to make a nice observation experimentally you put a glass slide at the top and put a microscope, or maybe at the bottom and put a microscope and see. This is very common experimental arrangement. See, that is why I always say that never try to become like a overt theoretician, that you do theoretical things but you lose completely the context. You may not be an experimental expert, but at least try to know what goes on in practice, because this is not a very sort of abstract theory like that people do not understand. This is something which practical things we are translating into mathematical language, which in maths is called as so called applied maths. So, now let us say this deformable material is a linear elastic material. In fact, these are all idealizations. In human body there are hardly materials which are like linear elastic materials. You will have some non-linear behavior, but for so many materials we can neglect it. So, approximately linear. So, let us say this is a model of a micro channel mimicking what is there inside the human body. The central line from which the y axis is there. So, you have this black line which is the deformed configuration of the wall when the fluid is flowing. So, we use two different coordinates, y for understanding the fluid mechanics and the zeta for understanding the solid mechanics. To understand that, we put a reference line, that orange colored dotted line. So, from there we measure that zeta, and capital H is the height of the boundary of the solid at any point of time t. It is a function of x, because it is not a constant, right, it is changing with x, and the whole problem is that you do not know how it is changing with x, that is the what you have to solve. So, we have put some notations. Ts is the that arbitrary if you consider that dotted line, from the dotted line to the upper rigid wall. So, it is physically the maximum solid layer thickness at that time, and H naught is the remaining. So, you have for a physical problem H naught plus Ts fixed, because upper wall is like a glass slide and it is rigid, central line is central line where it was. So, that gap is fixed, but in between there is a distribution of fluid and solid domain. Okay. So, for fluid domain what I have used is, I have used V for velocity. So, the continuity and the momentum equation, this is a micro capillary where the Reynolds number is very small. I told at the very beginning that the physiological fluid mechanics, you have a wide range of Reynolds number, from large arteries very large to these small ones like very low Reynolds number. So, we have neglected the inertia terms, the acceleration etc., and you have 0 in the left hand side and right hand side you have the pressure gradient and the viscous force, and you have the velocity gradient in both y and x, but because y is much smaller than x, the velocity gradient along y is much more important than that along x, and that is why it is that is neglected. This is called as lubrication approximation. So, you have two length scales, one is that small and another is large, and you neglect the gradient along the large as compared to the gradient along the small. Okay. In the solid domain, now this is that particular type of example where the solid domain is not physically accelerating, it is just deforming, like you have a beam in a structure. So, with load the beam will deform, but the beam will not physically accelerate, that it will not get out of your house and go to another house. So, that is what is this particular example. So, there is no body force, and therefore, you have just the simple this partial of sigma ij with respect to xj equal to 0. So, where sigma ij is written as you have the volumetric term and the deformation term. So, here we have used u for displacement and v for velocity. So, just you keep this notation in mind and then we move forward from here. So, now we are going to write an equation for the solid domain for I equal to 2. So, I equal to x, I equal to 1 is x and I equal to 2 is y. Can you tell that out of all equations why I equal to 2 is important? I equal to 2 means that y or zeta direction. See, overall you try to get a physical feel of the problem. The flow along x is important and displacement along y is important physically. So, whatever is that fluid solid deforming, its deformation is going to impact your solution more prominently along y, whereas the fluid velocity is along x. So, for fluid our main equation of focus is x momentum, and for the solid it is the equation of equilibrium along y. So, this is simple physical understanding. If you do not have this physical understanding, no problem, you write both all the x y equations and by considering the order of magnitude of the different terms you will come up with the same conclusion. But the use of physical intuition is that you can get rid of that toil and do it more from your physical understanding. So, for I equal to 2 we have just written that you have this partial of sigma ij xj is 0. So, we have put that j equal to 1 and j equal to 2 and that is the thing. So, now your j equal to 2, remember for solid mechanics we are using the zeta axis and along x is x axis. So, we have written this and we have written the expressions for sigma what is there here. So, you have sigma x zeta, this is the shear. So, the shear stress will not be dependent on volume change. So, that is why that volume term is not there, whereas sigma zeta zeta is the normal and that is where the volume change will be important, that is why the volume change is there. So, now you substitute that sigma in terms of this displacement u and try to get an order of magnitude analysis, that means which one is dominant and which one is not, which is also called as scaling analysis. So, if you do that all other terms will disappear except you will have this last term, and if your lambda and g are constant your simple governing equation is the second order partial derivative of u zeta, that means in the vertical direction displacement with respect to zeta is 0. So, this is in general not true, but with this lubrication approximation this you can get other terms which are not that important. So, now you come to the fluid domain and this is quite straightforward to most of you because fluid mechanics is more or less we have covered more. So, if you this is your equation. So, left hand side is 0 because acceleration is not important, it is a low Reynolds number flow, and the right hand side you have pressure gradient, and again for the viscous effect your y direction is smaller in length as compared to the x direction. So, if you have a micro channel y direction is micron and x direction is typically tens of millimeters. So, micro channels are typically quite long and very narrow in width or height whatever you call. So, in that way you can neglect that x gradient and then if you integrate it you will get the velocity. So, if you integrate it as you will get the velocity. So, one of the interesting things to note is that the constant of integrations are not real constants, they are functions of both x and t. Why? Because the only difference between this and the classical channel flow is classical channel height is fixed, and here fluid domain height itself is a function of x and t, and that is why the so called constants of integration are not constants, they are functions of x and time. So, this we formally call as partial integration. That means you are not really integrating it like a ordinary derivative, you integrate it partially where all other parameters other than y are like constant. and the boundary condition at y equal to 0 you have velocity gradient 0. So, y equal to 0 is the center line of the channel, we are assuming it is very symmetric at both the sides. So, you will get C1 equal to 0 and at y equal to h, and this is very important and that is why I have sort of put a asterisk there, h is not fixed, h is the height of the fluid domain small h, but it is not fixed, but whatever it is you have Vx equal to 0, this is the no slip boundary condition. So, you will get a C2, so you get a velocity profile and apparently this is like the velocity profile of a standard channel flow, only you have to keep in mind that this h is not fixed, it is a function of x and time. So, the golden question remains that I do not know h as a function of x and time, so how do I close this problem, because to get the velocity correctly I have to know h as a function of x and time, but yet we do not know, and that is where we have to couple the fluid and the solid. So, now for that we review the boundary conditions. So, we have used the boundary condition at y equal to 0, your velocity gradient 0, at y equal to h, which is basically zeta equal to capital H, you have Vx equal to 0 and Vy equal to 0, no slip, no penetration. At zeta equal to Ts, you have u zeta equal to 0, it is a rigid wall like the glass plate, there you have no displacement, and at zeta equal to capital H you have that continuity of traction or stress, right. So, that is what you have to consider, and this fourth boundary condition is very important because that is what which will couple the fluid and the solid mechanics. So, what we do now is we try to apply it with the help of whatever basic knowledge that I tried to develop in the early part of this session. So, we write the Cauchy's theorem. Now, you do not have n3 because it is a 2 dimensional problem, only n1 n2 are important, so it is a bit simplified. So, the Cauchy's theorem is written in terms of this just vectors and 2 by 2 matrix. For a 3 dimensional problem it is a 3 by 3. So, with that now you have, if you draw the tangent to the interface, so you have n1 as cos theta and n2 as sin theta, where theta is the inclination angle. When you have fully horizontal interface before the flow, before you have a flow and you have made a channel, so you have a wall and the wall is pretty horizontal, so you have theta equal to 90 degree, that means if you draw a normal to the wall its angle with the horizontal is 90 degree. So, you have n1 as 0 and n2 as 1, because n1 is cos theta, n2 is sin theta, the 2 direction cosines. But what we are trying to make use of, because I am trying to show you an analytical solution, and this is where you find that if the problem is having a large deformation, analytical solution is not possible. Why? Because for a small deformation we can make certain approximation that if theta is not 90 degree it is still close to 90 degree, because the deformation is not that much, so that n1 is still approximately 0 and n2 is still approximately 1, although it has deformed. So, with that you can write 0 and 1 for both the solid mechanics and the fluid mechanics, and you have tau 22 equal to sigma 22, where tau 22 the expression is there for incompressible fluid and for incompressible flow, and sigma also you have the expression, and the volume terms will go away. For fluid the volume term will be 0 because it is incompressible flow, and for solid anyway the normal stress expression you are, the volume term will be there, but we are assuming that the wall material is made of an incompressible solid, and typically with say therefore Poisson ratio equal to half. So, now the interfacial boundary condition if you put, see what we are putting in the left hand side is the normal stress. The normal stress has two components, one is the normal stress due to viscous effect, which is viscous normal stress, minus P, this is the normal stress, the standard hydrostatic, and the right hand side is the solid mechanics. So, you have a lambda and 2g. So, now what we are trying to do is we are not committing to that it is an incompressible solid. So, this is a bit of more generalized than what I told before as an example, because although it is hard to imagine for us, but many of the gel type of materials which are used for this biomedical applications, they are having some compressibility. So, it is not good to just take them as incompressible. So, whatever they have that G and lambda, so but for fluid the pressure is what is playing the deciding role. So, for fluid therefore, you have this minus lambda plus 2g, and here you see the displacement along x is not important and neither the gradient along x is important. So, in the right hand side the first term is small. So, this is where analytical work and numerical work is very different. Numerical work you do not use your sort of analysis to really tell which is small and which is large, but analytical you do, because then you can drop certain terms and you can simplify your work. So, you can then therefore combine the lambda plus 2g into the first partial derivative of u zeta with respect to zeta is minus p. So, remember that for the solid mechanics the governing equation is second order partial derivative equal to 0, and this is the boundary condition so called for the first order derivative. So, that is what we are doing. So, we are calculating the solid domain displacement. So, you integrate it and at so we are using two boundary conditions. Number 1, at zeta equal to Ts, that is the upper glass plate, you have u zeta equal to 0. So, that will give you C3 into Ts plus C4 equal to 0, and at zeta equal to capital H, which is the fluid solid boundary, you have this equality of normal stress. So, from that you can get the constants of integration and you get the displacement. Okay. So, now this has to be used and coupled with the what we call as fluid mechanics problem. So, you see that the major thing, the physical observation is the displacement is a function of the local pressure, and this is so intuitive, like if you have a blood vessel wall, how much the blood vessel wall will displace will depend on the pressure of the blood at that vessel, right. So, displacement of the solid is a function of pressure in addition to other properties, coordinates, etc. So, at zeta equal to H, capital H, you have u zeta equal to capital H. So, why it is so, just look into the diagram, let me just. So, at zeta equal to capital H, see that your u zeta is capital H. Why? U zeta is the displacement from that orange line, and that is itself capital H. So, in fact it is not a new boundary condition, it is just your geometry represented in a mathematical term. So, it is not a boundary condition, but we apply it. So, you substitute u zeta equal to capital H and this zeta equal to capital H, and you know that capital H equal to small h minus h naught from that diagram. So, now you get the fluid domain small h as a function of pressure. So, this is the crux of the physics, that you have a variable fluid domain where the domain height is a function of the local blood pressure or whatever fluid pressure. Now, you have to put a constraint if you want to couple the fluid and the solid. So, the physical constraint is, let us say there is a channel, the channel is deforming, means its fluid area is either increasing or decreasing, but if you have steady state the same flow is occurring. So, if you integrate the velocity over that h, where h is variable, you have the flow rate q which is fixed. So, if you put that, then you get a differential equation on p, because in the left hand side you have h as a function of p and you have the pressure as a function of x. We can also write it as dp dx, because pressure is not really a function of y, importantly it is also a function of y, but main variation is x. So, with this the last equation is giving you a governing equation of p as a function of x, and if you solve it, typically you do not have analytical solution to solve it numerically. So, you will get how pressure varies with x. So, if you get how pressure varies with x, because your small h is a function of pressure. So, you will get how your displacement of the channel boundary changes with x. So, you will get the profile of the interface of the fluid and the solid, that is the wall of the vessel. So, this is analytical, but it had many assumptions, like you have small deformation and maybe one of the dimensions, the width of the channel is much smaller than the actual thing. So, these things are not very what I would say general, these may be for some special type of problems, but not always. So, we have to solve the problems numerically, and some of the exercise problems that you will doing as a part of your subsequent lab sessions will reflect that. So, overall the numerical techniques, as I told, that you have some techniques which are called as grid based methods. Grid based methods can be fixed grid and moving grid. That means you can have a fixed grid and you can only sort of, or rather you are only finding out the location of the interface implicitly, but your grid does not change. Moving grid means you put your grid points on the interface, and as it is deforming or moving, those grid points will move. And there are many at least in the modern era, many computational tools which combine the fixed grid and the moving grid, and so this is grid based, but there are many methods which do not depend on grid. These are called as meshless or mesh free methods, and they are also getting very popular. And there are methods where you do not care about much this grid or mesh, you just focus your attention on what coupling is taking place at the interface and then solve the internal domain by some method or the other. So, that is known as interface coupling. Now, in the interface coupling you have two types of broad categories, one is partitioned and another is monolithic. Monolithic approach means both fluid and solid equations are formulated and solved together, and that is why it is very important to know their conceptual similarity. In the partitioned approach, fluid and solid parts are solved iteratively one by one, and then you couple them with weak coupling, that means fluid and solid at a time, or strong coupling, that means you divide your time step into finite time steps, and over some time step you talk about the this fluid interacting with solid and maybe another other part the other way. So, these are all there. So, if you get a broad overview of grid based and this or mesh based method or meshless methods. So, typically you have some elements, maybe finite element, as an example you can also have finite volume, control volumes. So, you have a domain in the fluid, you have a domain in the solid, and you have a boundary, and by some way you either move the points in the boundary, or how the boundary moves, you do not physically move that, but by some other way you reconstruct the boundary at every iteration. In the mesh free method there is nothing called as a boundary. So, you just generate a few nodes or particles, quote unquote particles, and you develop some shape functions on the local nodes in the support or structure domain. You discretize the governing equations and solve for unknowns at those nodes, but you do not care about physical concept of mesh or grid, and then you post process the results with some interpolation, so that you interpolate between the nodes without having a physical grid or a mesh picture into mind. So, these methods are getting very popular these days, the meshless methods, so to say. So, when you have such methods and when these methods are getting evolved, where we are moving forward, and this is very important, because as I told that when we are learning a subject, it is important to know the basic know-how, but where we can apply this for the futuristic research. So, I have identified a few pointers which are already very cutting edge active areas of research, but really not very impactful real life work. I mean of course modeling work has been done, but it has not really impacted so much the real life, because these are absolutely not very old methods. Like one is applying the machine learning model with these physics based models. So, you can use a fluid structure interaction model. Say in a very complex soft robotic system, you can use say how this system is evolving. So, let us say you have a solid and it is moving in a fluid, we have a Stokes drag law, Stokes law, this is physics. Now, when you have a soft robot and it is moving, you do not have such a law. So, how do you go about it? But if you have data on that fluid structure interaction, that data you can synthesize in the form of a resistance force theory, which will mimic a resistance force, which will be a data science driven simulator of something equivalent to a Stokes type of drag, and this is usually how machine learning is applied in fluid structure interaction problems. So, for understanding the swimming kinematics, that means how a soft robot is swimming. So, this is people have just started using it, this is very early development. Hydroelastic fluid structure interaction, so large structural displacement and nonlinear free surface flows. So, there is a method known as smooth particle element method. It combines with another method which, because of the interest of time, we cannot cover here, but very interesting method, smooth particle hydrodynamics, SPH, for flow modeling with the structural modeling with finite elements. So, it can in structural mechanics there can be many violent scenarios. Violent means large displacement. So, for example, you have a bridge and you have say some wind or some whatever load which is coming on the bridge, which is oscillatory in nature. So, you have a forced vibration. If the natural frequency of the bridge's material is same as that forced vibration frequency of resonance, and then it will theoretically vibrate with infinite amplitude. So, you have large amplitude motion possible. In the human body you do not have such a scenario, but you can have large displacement because of non-linear elastic problems. Particle based fluid structure interaction models, like they can solve complex cardiovascular mechanics problems like heart valve simulation to understand the behavior of the displacement of the blood heart, and how the heart valve, when it is sort of opening and closing, how it is impacting the overall dynamics that is taking place in a say heart, and maybe the myocardium, which is the heart muscle. Cellular mechanotransduction, very important area. So, you have the cells in the human body, the cells understand the signals biologically, but they transfer those signals mechanically. So, the biological signals are transferred into mechanical signals, and this is known as mechanotransduction. This is a very hot area of biology research, and this is where actually people can contribute. So, typically we have seen in many cases people are doing biology research with lot of experiment and is giving a lot of insight, but it does not have that mathematical flair. So, now if you can sort of try to have a fluid structure interaction modeling where you relate the deformation and the dynamics of the cell, which is the mechanical signal, how it is propagating, with the biological signal because of which the cell is deforming, and brain tissue brain fluid modeling. So, this is a very important problem, because this is a real serious problem when brain is not functioning, when people are in trauma or life support. So, if we are able to understand how the brain fluid is interacting with the brain tissue at that time, that can enable us to maybe get into conditions where by some means, by some medical means, it can be rectified. So, with that we come to the end of this, and I have we will share this with you. So, this is a homework practice review problem. So, you have I will tell you what it is. You have a cylindrical microcapillary. So, whatever I talked about as an example was a rectangular channel, and this is a cylindrical channel. So, you are given that its radius is changing along the axis because of some fluid structure interaction. So, you have the original radius A plus the displacement UR, and it is described by the properties modulus of elasticity or the Young's modulus and the Poisson's ratio. We assume that it is thin, the wall of this is thin, and therefore, you can use thin walled pressure vessel as a solid, or you can say mechanics of material, or in undergraduate text also known as strength of materials model, as a thin walled cylinder or thin vessel model, where the stress and the strain are written in, they can be written in terms of the pressure. With this you have sigma theta theta, which is the hoop stress or the circumferential stress, is A by T into P. So, and P is the pressure. So, if you know the stress, you can calculate the strain, that means the displacement you can formulate as a function of pressure, and then you can solve the entire problem just like what we have done, except the coordinate system here is a cylindrical coordinate system. So, 4 parts, or rather 5 parts of this problem is there. Essentially write the governing equations for flow and find an expression for velocity, find an expression for pressure gradient, and integrate it to find out the pressure as a function of z, and compare this pressure. So, you have a pressure as a function of z. If you have just a circular pipe or a tube or a channel, pressure versus z is linear, dp dz is constant. So, you can compare that with this, and that will give you an idea of the impact of the fluid structure interaction in creating a change in pressure. Okay, so, and this is purely analytically pen and paper you can do. So, we have mixed all the lab work and assignments with something you can do in pen and paper to create your understanding, and in a computer to translate that to solve a practical problem. Okay, then, so we close this here, and we will then move as per schedule the remaining parts of this.